Hello everyone. In today's session, let us learn about queuing model 3, where in the past two videos we learned about your model 1 and model 2. Okay, so now we are just going into the model 3, where it is a multi-server model with infinite system capacity. Okay, so where the service is going to be more than one servicing channel, more than one, and the capacity also infinite, right? So next, we'll be looking into the terminologies here as usual. So yes, parallel server will be there, Markovian arrival, exponential service time, and we have unlimited waiting room here, and the number of customers will never turn away because of the room is full. Okay, and this discipline, what we follow here is first in, first out service discipline. And as usual, the customer arrival will be following the Poisson distribution with the arrival rate denoted by lambda. And the service rate here follows exponential distribution with the rate of mu. The denotation is mu. And the traffic intensity here it is followed with lambda by S mu. Whereas the fast both the model, your lambda will be the scenario of lambda is equal to, that is your rho will be lambda is equal to sorry, your rho will be mu is equal rho will be lambda by mu. This will be the traffic intensity for the single server model. Whereas where this is single server model with infinite capacity or else a finite capacity, whatever it is, your traffic intensity is lambda by mu. Whereas for your model here, which is with the finite capacity, with multi-server, not finite, which is the multi-server model, we have the restriction with your traffic intensity is lambda by S mu. S mu is with nothing but the number of service, parallel service available here. Okay, and the condition for the steady state rho should be less than when the total service rate S mu must exceeds arrival rate lambda. Okay. So let me go with the key formula for computing the multi-server model with the infinite capacity. So we'll say it as M with the S multi-server with the infinite capacity with the discipline FIFO. So the first, as usual, the probability of empty system, that is no customers in the system, is given by P naught is equal to summation n is equal to 0 to S minus 1 by n factorial lambda by mu the whole power n, and this is summations for this term alone, not for the rest, because we have n only for these case. Okay, you should be very careful when you are calculating P naught when you identify this problem as a multi-server problem, and based on calculating for n varies from 0 to S minus 1, then you have to cumulate, add with lambda by mu the whole power S upon S factorial 1 minus lambda by mu S whole thing to the power of minus 1. Okay, not only for this term, the entire thing. For the entire, it is lambda minus 1. It is like 1 upon this term. Okay, so where S denotes the number of parallel server and lambda is a Poisson arrival and mu is service rate, exponential service rate per server, and condition for your steady state is your traffic intensity should be less than 1. Okay. So coming to the next formula of your customers in the queue or anything. So when it is like your case of 0 less than or equal to n less than n, few customers than the service served. The number of service channels is more, and if it is less, no queue, then your Pn is 1 by n factorial into lambda by mu the whole power n into P naught. Okay, for when the customer is less than the number of service channel available. When n is greater than s, when the number of customers available is greater than the number of service channel, then the queue is formed. So that we have to calculate here accordingly what is here Pn. So Pn is 1 upon s factorial s to the power of n minus s into lambda by mu the whole power n into P naught. Okay. So coming to the performance metrics here, the other scenario formulas like calculation of the probability of all server busy. That is, we will say the server is busy, right? So it is nothing but when all the server is busy, we have to calculate the probability. That is, probability of n greater than or equal to s is equal to lambda by mu the whole power s into p naught by s factorial into 1 minus lambda by s mu. Okay, and the number of customers in the queue is nothing but LQ upon LQ is equal to lambda by mu the whole power s into P naught upon s into s factorial into 1 minus lambda by s mu the whole square. Okay, and average number in the system. LS is nothing but based on LQ it is calculated using little formulas. LQ is plus a lambda by mu, and average waiting time in the queue is WQ is equal to LQ upon lambda, and average time in the system is WS is equal to WQ plus 1 by mu. Whereas in the whereas in the second model we use traffic intensity lambda dash. Okay, but here we use just the traffic intensity is effective traffic in arrival rate. Instead of lambda, we'll use effective arrival rate wherever use traffic intensity in the little formula for the model 2. What is model 2? The model 2 is a single server model with a finite system capacity with a discipline of F1, F5, F2, first in first. Whereas here we will use only just lambda, the lambda by mu, it is traffic intensity here, and lambda is arrival rate and mu is service rate. These are called the little formulas. Okay. So with this only we are just going to operate the problem. So let us look into the problem next. So first type of problem. There are three typists in an office. Each typist can take an average of 6 letters per hour. And if the letter arrives for being typed at a rate of 15 letters per hour, that means each letter is getting serviced at a rate of 15 letters per hour. Per hour, the typist can type 15 letters. So, service getting with the letter is since it is serviced. And now, what fraction of time all the typists will be busy? So, the probability of the server is busy. And what is the average number of letters waiting to be typed? So the number of letters waiting to be typed in the sense that Q. So average number of letters. So LQ has been asked. And what is the average time a letter has to be spent waiting and for being typed? So it is nothing but we have to find for waiting in the queue. As usual it is typing. So for the entire system we have to find the waiting time. So we have to find WS. Okay. So now let me first, what is the given one? 3 types. So number of service channel is 3. So service channel S is 3. And each type is type an average of 6 letters per hour. So 6 letters per hour he can type it. So here the mu is 6 per hour. He can type an average of 6, and if the letters arrive for being typed at a rate of 15, so number of letters arrived per hour is arriving, so this arriving rate is lambda is equal to 15. So typed in the sense it is serviced. Sorry, I have been mistakenly saying type is the service getting and arriving is just getting in. Okay, so I have specified wrongly. So excuse me. So it is like arriving per hour 15 letters. So arriving is 15. And getting service here is typed. Typed here it is Per hour, typist can service 6 letters, type 6 letters. Okay, and the traffic intensity, as usual, here traffic intensity is lambda by s mu. So lambda is 12 and s mu is 6 into 50. Okay, so what is the first thing that all the typists will be busy now? So it is probability of n greater than or equal to yes. So probability of n greater than or equal to x, we know it is the formula like we have it, that is lambda by mu. So it is lambda by mu. Okay, so whole power s into p naught, the whole thing upon s factorial 1 minus lambda by mu s. Okay, so here we know we want p naught. So let me calculate p naught. So p naught is n varies from n is equal to 0 to s minus 1. So it is 0, s minus 1 is 2. So 1 by n factorial. So it is given, it is 1 by n factorial. The formula here it is 1 by n factorial into lambda by mu the whole power n plus lambda by mu the whole power s upon s factorial 1 minus lambda by mu s whole thing, the entire thing to the power of minus 1. You people will be making mistake on taking minus 1, the power of minus 1 only. So when you're just calculating this P naught in model 3, you have to be very clear, very careful in doing with your P naught. Here, once you're doing your P naught wrong, then everything goes wrong. So be careful when you identify the problem. This is type 3, which is multi-server model. Be very careful when computing your P naught because you have to be first very cautious in finding your summation values of this one. Okay, so then you have to add it with the rest of. Then finally you have to make it of minus 1. So you have three parts in doing a P naught. First, you have to go for the summation values first elements, then find the values of this one, add both the things, then take a power of minus 1. So then it will be giving you the final answer is 0.0449. So now I'll go and find my when n is greater than the server. So it is calculated according to the value of lambda 15, mu 6 and S3. It is 0.7016 and the question, the fraction of time, you have to give it in a percent. So 70.16 percentage of times all typists are busy. Okay. So second, what is the average number of letters waiting to be typed? So LQ. So LQ is lambda by mu the whole power k s plus 1 into your P naught and s into s factorial 1 minus lambda by mu s the whole square. So the average number of letters waiting to be typed LQ is 3.508 letters. And what is the average time a letter has to spend waiting and for being typed? So it is WS, whole system waiting, right? So WQ plus 1 by mu. So LQ is equal. WQ is nothing but again now we have the formula, right? It is LQ upon lambda plus 1 by mu. So we know what is your LQ, what is your lambda, and what is your mu. So substitute it. So you'll get the answer is 0.4005 half hours. So finally, we calculated what is the fraction of time all the typists will be busy and what is the average number of letters waiting to be typed and the average time a letter has to be spent in the waiting as usual to be typed. Okay, that's it. So now let me go for the next problem. So a petrol pump has four pumps. The service time follows an exponential distribution with a mean of 6 minutes. So service time, it is given in minutes, so we have to convert it into hours. So it is like this case. It is we'll be taking as mu is equal to 1 by 6. So convert it into hours. So you'll get it as 60 minutes. 10 per hour. Car arrives for the service in the Poisson rate of here 30 hours, 30 cars per hour. So it is directly given in hours. So 30 slash 30 per hour. And what is the probability that an arrival will have to wait in the line? So we are waiting in the line, so that means n greater than or equal to s. We have to calculate with probability of n greater than or equal to s. And find the average waiting time in the queue. So in the queue, waiting time in the queue is LQ. And find the average time spent in the system. So WS we have to find. And find the average number of cars in the system. So you have to find it, yes. So first we have to find probability of n greater than or equal to yes, and here we have to find LQ, and here we have to find the weighting in the system. Okay, so all before we start with this, we have to compute your P naught. So it is involved in the formula of the rest of the case like LQ, WS, everything. Okay, so P naught is as usual said summation n varies from S minus 1. So S minus 1 is 3 because S is 4 here, so S minus 1. So first calculate this part. Okay, then calculate this part, the second part of the formula, then add these two things, then take 1 upon that will give you the value of 0.0377. And we'll go with the formula of P of n greater than or equal to 4, where it is lambda by mu whole power s into P naught upon s factorial into 1 minus lambda by s mu. So which gives you the fraction of the probability arrival has to wait, right? So it is 50.9 percentage of probability is waiting. And coming to the next, it is find the average waiting time in the queue spent in the system is like waiting time in the queue. So it is like the second one, waiting time in the queue. So you have to find a WQ. So to go for the WQ, we don't have the direct form we have, but we'll use the shortcut of LQ upon lambda. So it's not WQ LQ, it is WQ waiting time, right? So we have to find waiting time here. Also, time waiting is given, but this is an average number, so that's what it L. So it is like LQ is 30 upon mu lambda by mu the whole power s plus 1 into P naught upon s factorial into s into 1 minus lambda by s mu whole square. So on calculating we'll get LQ is this thing. So with this we can calculate what is your WQ. So LQ upon lambda is 1.527 upon your lambda. So you have the waiting time in the queue is 0.0509 hours. So next thing is finding the waiting time in the system. WS is WQ plus 1 by lambda, which is 0.509 plus year 1 by 10. So you'll get what is your WS. And similarly, I can find what is the average number of cars in the system. So which is in scenario LS is equal to LQ plus lambda by mu. So already we know what is your LQ, and lambda by mu is this thing. So finally, the average number of cars in the system is 4.527 cars approximately. So this what we have to go for the problem solving. So whenever you identify the problem is a unit uh, in the QA unit, this unit model 3, you have to initially find what is your lambda, what is your mu, what is your service channel number, and then start calculating your P naught, because you want P naught to go for computation of the rest of average time or average customers or average waiting time or waiting in the queue or everything. Okay, so you calculate that and then go for the calculation of the rest of the requirement. So this is a quick reference of your formula. So P naught is this thing, and Pn when n is less than s, this will be the scenario, and Pn when n is greater than s, this will be the formula. And we have the case of here S mu, that is n greater than or equal to s, that is not probability of n greater than or equal to s. This is Pn, calculation of Pn when n less than s and n greater than or equal to s. And when we have to find the probability when the number of customers is greater than the service channel, we have to compute using this formula. And LQ is number of average number of customers in this queue, as lambda will be the whole power is P naught upon the denominator. And L is the average number of customers in the system, is calculated based on your customers in the queue. And WQ, average number of customers, waiting time of a customer in the queue, which is calculated based on your LQ. And The average waiting time in the system is calculated based on your WQ. These are all calculated using your little formulas. Okay, so with this, we end our session today.